It's my pleasure to introduce to you now our second speaker of the session, Marcela Carena, who I think very soon will be permanent if you aren't ready yet.
Already.
Already, okay. And she'll be telling us about baryogenesis in the early universe.
Okay, thank you. First of all, thank you, Katie, for inviting me here. I'm very pleased. Second, as many of you, especially the theorists, know the Perimeter Institute, I have taken the crazy challenge of be the next director. I started 9 days ago, and 2 I have been here, so okay. But what I, yeah. Sorry, the talk has been done at the last microsecond, so apologies for that ahead of time. But what I want to say is that you are all, next year, we are starting December 12th to celebrate the 25th anniversary of the Perimeter Institute. And so many of you have been there and know the place. I warmly invite you to think about coming and visiting us, maybe not in January, but I don't know, to visit us during the next year. We will have celebrations the whole year, and you will be receiving invitations. I just discovered that people were running a bit relaxed on that, so I'm putting my people to work now. So stay tuned, please. Stay tuned and consider to come to visit us, okay? Okay, so without further ado, I will talk a little bit about baryogenesis in the early universe. I love that I put all my institutions there. I'm still connected with my heart and my soul to UChicago and to Fermila, and also with the developments. Okay. So anyways, the outline is what I will try to talk to you about today is, of course, we all know that there is the problem of explaining what is the matter-antimatter asymmetry of the universe. And today I will concentrate on how it gets connected to the Higgs field and the electroweak phase transition. So first of all, I will first remind you, since I think this audience is very diverse, and by the way, I'm excited of this energizing set of talks that we have had all the way. I will remind you a bit about electroweak baryogenesis in the Weinberg standard model, and I will tell you why it doesn't work there, okay? And then I will try to tell you a bit of how we can think going beyond to really think about electroweak baryogenesis. And I will only touch very briefly upon these 3 models, but the reason for that is that each of these models will be an example of a problem that we have to deal with and how we can solve it in this scenario. Okay, so that's why these models are there. So electroweak symmetry breaking and the phase transition, as we all know, already almost 12 years ago, we discovered the Higgs, and that put, like, le beurre sur les épinards, so the extra point over the standard model of particle physics. But also, it brought new insights to our total ignorance about electroweak symmetry breaking and the electroweak phase transition. So in some way, put it up into context. So let me just remind you that the reason that we are here rather than here today, if it were today the energy, is that we put by hand in the standard model the condition of electroweak symmetry breaking. And what it means is that we are really putting this mass parameter with its negative value here, and these quartic couplings are all put by hand in some way in the standard model, and then we fit it to what we observe. So the question is, what is behind the mechanism of electroweak symmetry breaking? In this audience, I know there are many people that love supersymmetry, especially Ken, I don't know if he's around. But in supersymmetry, we try to solve the issue of electroweak symmetry breaking by quantum electroweak symmetry breaking, by radiative corrections. And I won't go into detail, but it's a very beautiful solution. Or we can think that there is some compositeness of the Higgs, and of course, if you think about bosonic states in condensed matter, it's very natural that you get composite states that will trigger phase transitions and symmetry breakdown. So what we want to understand is what is the history of the electroweak phase transition that happens, so to say, instants after the Big Bang. So the Higgs discovery, so the Higgs field is turned on in these moments after the Big Bang, and we know that the electroweak phase transition took place, but we don't know about its dynamic, and this is what we are trying to explore. Again, so today I will concentrate on this idea of what we call electroweak baryogenesis. So I don't need to tell this audience that from precision cosmology, we have a very good information about the baryon abundance. And the question is, was it generated from, what generated it really? So was that some initial condition or some process that occurred there? Of course, we are advocating for the second. Of course, there are many people that ask this type of questions. And in fact, it was mentioned papers and thoughts of Weinberg, Steven Weinberg there. The first one, as far as all we know, that postulated what are called the three Sakharov conditions. This seems that is a very nice, I have never seen it myself, but it's in some place in Russia, this nice sculpture, thank you. So first of all, these are the three Sakharov conditions. Baryon or lepton number violation, if we start with a symmetric universe. Charge and CP violation, and this is because these treat the baryon and antibaryon differently, and we have to be able to remove antimatter, and I will go into that in a second. And finally, we need to be out of equilibrium, basically, in a nutshell, in order to suppress the inverse process. So the careful, so what we are asking is, can successful electroweak baryogenesis occur involving the Higgs field? How does it take place in the Weinberg-Salam standard model? And for that, I will go in a second in that we have to first generate the baryon asymmetry at the electroweak phase transition, and then we have to secure the conditions to preserve that baryon asymmetry that we generate at the electroweak phase transition so that it is today the value that it is, okay? And this is what has to do with the strength of the phase transition. And this has to be done, of course, for the standard model within the standard model particle content. And this is what we discuss. So let me just remind you the basic things in the standard model. So condition, Sakharov condition number one, breaking baryon and lepton conservation. As you all know, after quantization, the standard model conserves B minus L. And this has to do with the fact that in order to preserve or to make an anomaly-free quantization of the electroweak gauge symmetry, in order to preserve that, by the same token, we are preserving what would have been the B minus L anomaly. So it's by construction in the standard model, we have B minus L conserved. However, B plus L is not conserved, is because of the quantum anomaly. And this is a very nice picture, I like it. So this quantum anomaly is related to this existence of these winding numbers. They are called Chern-Simons, as you know, winding numbers that relate the general states of the SU2 left gauge fields. And these are separated by this barrier. At the top of this barrier is what we call the sphaleron. So these anomalous processes are the ones that create, this anomaly create the processes that lead to non-zero baryon and equal non-zero lepton number. And if you look this, the non-conservation of the baryon and lepton currents are related in this way to the SU2 gauge fields, and the SU2 gauge fields are, so this is what appears in the definition of this Chern-Simons number. This is because of the three, of the three generations. So these sphalerons here, these blue dots, are gauge and Higgs field configurations, and these approximate the transition. So it's a static configuration of what would otherwise be an instanton tunneling. So it's a static configuration that allows us to go over the hill from one winding number to another state. So at final temperature, these sphalerons process are have the usual Boltzmann suppression. So this is the baryon number violation. But the important thing is that the energy at the top of the barrier is proportional to the vacuum expectation value of the Higgs. And that's really what matters, okay? So because we are going to get a lot out of that the baryon, the energy of the sphaleron is proportional to the Higgs BeV at the temperature that we are looking, or at zero temperature would be. At zero temperature, at very high temperatures, the vacuum expectation value of the Higgs is 0 because we have symmetry restoration, and therefore these baryon violating processes are highly unsuppressed because this is just not there. But when we have very at zero temperatures instead, these baryon number processes are highly suppressed. And so we are going to be looking at temperatures that we are defining in a moment to be critical temperatures. Okay, so the second Sakharov condition is charge and CP violation. So CP violation, as we all know, occurs in the standard model from the CKM phase. We don't know if in the leptons occurs as well, but we expect that. So as a result of this quark CP violation, there are processes such that the left-handed, I call it up here, but it's any of the quarks, of course, the up type quarks. So the up quark going into right, or the anti-up quark left going into the anti-up quark right, these cross sections can be different. And as a result, we can generate an asymmetry in the left-handed sector and an asymmetry in the right-handed sector. I remind you that this left, this is like when you think about, we have seen left-handed neutrinos, and therefore right-handed antineutrinos, okay? So this here is a right-handed antiparticle, but the left subscript here is because it's an SU2 left doublet, okay? So we have this asymmetry here, delta L, and we have delta R. What is important, we are going to generate this with CP violation, but in the absence of charge conjugation violation, so charge conjugation violation would tell me that this density U left is equal to this density anti-U right, okay? So in the absence of charge conjugation violation, what happens is that delta L is equal to minus delta R, okay? And this means that there are two pieces in this idea of generating the baryon asymmetry. One is that we generate some charge parity violation number here, or asymmetry. And the other one is that before the sphalerons, before we have charge conjugation violation, delta B is still 0. So we have not generated any concrete baryon number, okay? So first step, we have to generate some CP violating asymmetry, and second step, the sphalerons will come and help us to generate the baryon number. So as we shall see, the sphalerons will do the job of generating a charge conjugation asymmetry, and because of that, because they are really only looking at left-handed quarks and left-handed leptons. So sphalerons are SU2 left particles, they don't see left-handed or SU2 singlets, okay? So right-handed particles. Okay, is that clear? It's so many different, the audience is so different that for some people this would be totally trivial, and for others, maybe they think about it. Okay, so the third condition is the out of equilibrium, and this is what we call the first order phase transition, where we have bubbles of what I call Higgs on, which means the Higgs has a BeV, and this is our true vacuum at the end here at 0 temperature. That is, these bubbles start to form in the plasma of the false vacuum of Higgs off, okay? And so the first order electroweak phase transition is when the universe really tunnels from a vacuum expectation value of the Higgs equals 0 to the vacuum expectation value of the Higgs different from 0. So it goes from here to here through tunneling at some temperature, okay? And we define the critical temperature. This is important for what I want to say. The critical temperature is the temperature at which the value of the potential at the fake value vacuum is equal in depth of the value of the potential at the true vacuum. Okay, so this is defined with critical temperature. Okay, so the bubbles nucleate and expand in the presence of the plasma of standard model particles, of massless standard model particles. The bubbles move near the speed of light, And this, of course, will depend on the frictional force of the plasma particles that are exerting on the bubbles. And for that, the precise bubble wall velocity is very relevant. And in fact, is part of what I'm going to talk about, and is part of what I'm working on very actively at the moment, is to understand how to compute from first principle the bubble wall velocity, because the bubble wall velocity at the end of the day will play a crucial role in which is the actual baryon number that I generate, and also will play a crucial role in gravitational wave signals from first order phase transitions. Okay, and we have heard a lot about gravitational wave signals today, and I will try to tell you from a little different perspective, but this is crucial. So when we have to make the whole thing work, okay? So, so the process near the bubble wall are very high out of equilibrium, and the CP violating dynamics, I'm going to that in a second, is occurring basically at the bubble wall, okay? So this is what we see, or this is a bit going, this is making a lot of noise, but I don't know what to do about that. Huh? Here? No. On my shirt. You think I will not move so much. That's better? Not sure, but okay. But you know what? I have a skirt today instead of a dress, so maybe. It's okay, it means it's worse, so thank you. It's okay, I will try not to move too much. I can't. Okay, so this is better. CP violating effects and how we generate the baryon number at the electron phase transition. As I told you, we are assuming that there's nothing there. We are generating it from scratch, okay? So that's the idea of electron baryogenesis. So there are CP violating effects at the bubble wall, and those effects are really induced by the Higgs quark interactions. One of the issues there that I want to tell you is that we are using the CKM mass matrix, but of course, the Higgs quark interactions we really care about are the Higgs with the top, because are the strongest interactions. And there is where the issue comes, that the CP violation appears at higher groups, okay? Just for you to keep in mind. But anyways, so the CP violation is induced through the Higgs quark interactions when particles flow, and some of them are transmitted, some of them are reflected. This is also a subject that I'm working very actively on and trying to use quantum information ideas to do better calculations. And I think John is also very an expert, much more than me on this topic. So the particle flow into the expanding bubble wall will create a chiral asymmetry. And what happens is that we have an excess of SU2 doublet antiquarks, and therefore SU2 singlet quarks, which it means just outside the bubble wall, which it means is that we are going to generate some delta L and some delta R. As I told you, delta B is all equal to 0. So this is what I'm generating outside, just outside the bubble wall. Then here, my sphalerons are active. Remember, I told you this, the sphalerons become inactive here, and they are exponentially suppressed here, but the sphalerons are still active here. And what the sphalerons job is to violate B plus L. So they take any antiquarks, 9 antiquarks, and they change it into 3 leptons, and they do quarks into antileptons. These are my sphalerons. But because of these, because there are more antiquarks than quarks, this process is faster. And so at some point I have to shut this off, because if I let that to the end of the process, then I will end up washing out everything. So that's one of the conditions that we will go back. But in the first point, what I'm doing is that I basically use my sphalerons, so that before the sphalerons, this guy is equal to this guy, and therefore delta B is equal to 0. But then the sphalerons do this process, but I told you that the sphalerons only see left-handed particles. So they only touch the left-handed side of this equation. And so that means that the sphalerons come and do their job in this quantity F here, that you have to compute it carefully. So basically, the total baryon number at the end after the sphalerons, with the sphalerons doing this only for the left-handed, we generate basically some positive, and you have to define it properly, some positive excess of quarks over antiquarks outside the bubble here, okay? And so, as I said, the next step I will tell you if we have to do that in a way that we freeze it in so that we don't let the whole system relax and go to zero. Okay. So the Higgs discovery, of course, supports the occurrence of this electroweak phase transition, but then we have to look more carefully because, as I said, we need to shut off quickly this process to prevent the washout of the asymmetry. And if you do the calculation, so what I computed there, let me tell you that this is at T critical. I will go in a second and tell you that this is at T nucleation, but for the moment, just T critical was the point where the vacuum, the true vacuum and the fake vacuum have the same depth, remember? So at this, I have done this calculation in the previous slide, and I got my value. Let's say I got the value I want to explain the baryon antibaryon asymmetry. So I need, by doing the evolution, the evolution of this baryon density, if I do the actual calculation, I get this equation, and this equation really is only, if you do this, it's just making the balance between the expansion, the Hubble expansion, and the baryon number violation rate. So when the baryon number violation rate is smaller than the Hubble rate, then the baryon number violation process are frozen. And this condition put inside here means basically that all this term is much lower than 1, which means that whatever I create at T critical is what I have today. This is today. Okay? And so this is a process that requires that the vacuum expectation value of the Higgs over the critical temperature has to be, sorry about that, of the slightly larger of order 1. And this is the condition of a strong first order phase transition in order to preserve the baryon asymmetry that I have generated. Okay? So basically, this is what it says here. And the caveat that I will probably, I have totally lost control of the time, but okay. So what happens is that in reality, what matters is that we can have this critical temperature, but what we really need to compute is the nucleation temperature, the moment in which, at least per Hubble volume, per Hubble time, I have generated one bubble. Okay, and it's a way to define this nucleation temperature. It's much harder to compute this nucleation temperature because you have to compute the bounce action, which means that you have to look at your two minima, and when there are multiple scalars in your, multiple directions you can go to, is very hard to compute, which is the most efficient path to go from one minimum to the other to compute the actual Euclidean action that minimizes the path. So, but we need to compute T nucleation in reality, and in some cases, as in cases that I will show one example in supersymmetry, is important, this difference. But usually one plays with this because it's much easier to compute. Okay, so failure of the Weinberg standard model for baryogenesis, actually, only. It doesn't work, and in fact, I think Steve Weinberg was one of the first that thought about, starts saying something about this. So the standard model has all the ingredients we need for the Sakharov condition. Has baryon number violation through the sphalerons, has CP violation through the CKM mass matrix, and has an electroweak phase transition that could have been strongly first order. Is not, but could have been. So why this doesn't happen? The first thing that is screwed up is the CP violation. In fact, as I mentioned, we have the Yarros invariant, and we can compute, which is proportional to the CKM mixing angles, and we can compute, what matters is that there is a contribution, a CP violating contribution, effectively to the mass of, to the top quark Higgs interaction. But this complex top quark Higgs interaction in the standard model only appears at 7 loop order. And that's why when you do all the calculations, which was a topic of very, that was the first time I was a postdoc at CERN, and was the first time that I was seeing Belén Gavela and Misha Shaposhnikov going to eat each other about a calculation. And because Belen had a calculation that was 10 to the minus 20, and Misha had a calculation that was 10 to the minus 10, which would have been a very good result, okay? I think it's Belen who won. But in fact, while preparing this talk and while talking to my student yesterday night very late, I realized that this value is the value that was computed in 1994, and probably a couple of orders of magnitude would be changed because we have improved our calculations a lot. But I don't think that we can really make a change at the level that we will go to 10 to the minus 10 as we need. So the second problem is the Higgs mass. The Higgs mass is just too fat, too heavy, okay? So you can compute this VT over T critical if you do perturbative. This really goes like 1 over the Higgs mass. And so the Higgs mass should have been lower than 40 GeV perturbatively. And if you look at these lattice calculations here, the standard model is a crossover for values of the Higgs mass 125 as we have measured. Okay, so what it means is we cannot generate enough baryon number asymmetry. And if we would have been able to generate it, we have not been able to keep it up to today in the standard model. So we need something new. Okay, so electroweak baryogenesis needs new phenomena, as I said, to provide new sources of CP violation so that we can generate the right baryon asymmetry. So we need new sources of CP violation. And we need something new to make this a first transition, a strongly first order. Are you sure? Oh boy, I'm in deep trouble, but okay. Okay, so I'm half of my talk and only 5 minutes left. So the idea is I wanted, so there are many models to do that. And I know Weinberg didn't like models, but still, the simplest model that I want to say in a few words is just adding one singlet. Why I do that? It's not a realistic model, obviously, it's a toy model, but it's to show how easy it is to make the phase transition strongly first order. Okay, so let me just show here the basic ingredients. So now our potential, besides here, the Higgs potential I showed you before was these 2 pieces. Now I'm adding a singlet and the interactions of the singlet with the Higgs. Okay. And let me not go into the whole song and dance here, but let me just tell you that in order to determine the phase transition, one has to compute, of course, temperature and quantum effects of this potential. And in fact, you will laugh, and I was laughing at myself. So the quantum effects at 0 temperature, this is a temperature because it has to do with AC resonation, so forget it. I mean, it's right, but I won't go into that. So this is Carena and Weinberg, but it's the other Weinberg. So, but anyways, I was going to make a story about the Carena and Weinberg, but no. However, this is Esteemed Weinberg, which I did not have the pleasure to know him, but listening to John's talk, I was very enlightened about his personality. So, in fact, this part, that is the final temperature piece, has been first discussed in the seminal paper by Steve Weinberg, who was thinking about these symmetry restorations at high temperatures. Okay, and this is a very, I mean, many other people have looked at this effective potential. But the important point, if you put just this one very simple addition that is a singlet, is that at final temperature, first of all, you see here there's a temperature-dependent piece on the mass. And this is the responsible for the symmetry restoration when this whole term becomes positive at high temperatures. And this term that has a phi cube or h cube term is the one that gives me the slope in the potential, the little mountain, sorry. And so that you can, you have to channel into it. So this is what allows a first order phase transition. And so let me just go very fast and oh boy, I went so fast that I lost one slide. That's so funny. I lost the slide. Okay. That's great. Boy, okay, I lost it. Anyways, there is a slide missing, but we can analyze this potential here very carefully, and we can look at what is V over T larger than 1, and it happens that this potential depends a lot on many phenomenological issues that has to do with how much the new scalar mixes with the Higgs. Of course, LHC puts a very strong bounds on that, okay? And altogether, you can see that you need the new singlet to be sufficiently light, and the mixing with the standard model Higgs to be sufficiently sizable to change the strength of a phase transition. And this has a lot of good properties. The one thing I didn't say, electroweak baryogenesis is exciting because it's at the electroweak scale and therefore has a lot of falsible or of testable things that we can see at different experiments, and in particular at LHC. So let me just tell you that if I look at the branching ratio of the standard model Higgs into the singlets as the mass of the singlet, all this area here is what would give me a strong first order phase transition. And this area above here is what the high LUME LHC will probe. And we will need a Higgs factory in order to understand if this model is true or not. But the important thing with this is to show you how easy it is actually to change this strength of a phase transition, even with one singlet, okay? Because of, well, the one thing I want to say then is that I think for these audiences of interest is that once we have this first order phase transition, we are expected to have gravitational wave signals, okay? And this I think is exciting. So what we look is that we have to look, this equation of motion has the scalar contributions, and this is the friction term that has to do with the plasma dynamics. And this is an equation you can solve by considering the conservation of the divergence of the energy momentum tensor. But the important thing here is that you can express everything in terms of this effective potential that I showed you before, okay? So basically, once you compute your parameter in your model, whatever your model is of the Higgs interacting with other particles, you can come and consider what would be your gravitational wave signal. And that's what matters. So then there is, oh God, okay. So basically we have three sources for gravitational waves. One are the collisions of the bubble. The other one are the contributions to the gravitational wave from the some waves of the plasma. And the third one is the plasma turbulence. This I think is the most unknown, and I really know nothing about it, so I have followed the literature there. But we have these contributions. The important thing here is that these bubbles can have what we call this gravitational wave, this bubble wall velocity can be a runaway bubble. And in that case, what happens is that the plasma effects become irrelevant and all what matter are the bubble collisions. This, however, intuitively is not, you can see it intuitively, is not what we want for electroweak baryogenesis, because I told you that these sphalerons have to do their job outside the bubble wall. And if the bubbles are having a runaway velocity, things happen so fast that there is no time for the sphalerons to do their job, basically, okay? So the point that the case of interest is when there is some terminal velocity. And therefore, there is a sizable friction from the plasma, and the two contributions that we have is the sound wave and the turbulence, okay? And this has been computed, and I will show one example if you give me 1 minute more. So it is important to compute the bubble wall velocity from first principles, and this was done already in this paper of Lauren and Klein. But the important thing here is that the bubble wall velocity is going to define if this first order phase transition will give us a strong gravitational wave signals. It's not the only component. So the three parameters that define the gravitational wave signals are the inverse time duration of the phase transition, okay, the bubble wall velocity, and the strength of the gravitational wave signature from the phase transition. That, as you see, this dependent on the vacuum energy between the symmetric and antisymmetric vacuum with respect to the radiation bath. And again, this is dependent on the effective potential. So once we have our model, we can compute the strength of the gravitational wave. This is an example for the simplest model where we compute the gravitational wave signal as a function of frequency. So The frequencies are here in this range, and you can see how it works for Lisa and so on. So again, the computation of the bubble ball velocity, which here we did, is decisive. As you see, when you could compute this gravitational wave signal, the bubble wall velocity appears in a very decisive way. So since I don't have a lot of time, I will skip completely supersymmetry. I'm sorry for Kane. No, sorry. That was especially for other people, the supersymmetry, but I will miss it. Is Kane around or not? I don't know. No, okay, good. Okay, so there is one thing I want to tell you, and let me just show you this, okay? Not so long ago, my students and I, we proposed a good solution, and so let me leave you with this. My chair, don't get too nervous. So I told you that it's very important to have new sources of CP violation, okay, in order to generate the right baryon asymmetry. The problem is that if we are generating new sources of CP violation, we have beautiful experiments of measuring, for example, electric dipole moments, which actually put a strong bounds on CP violation. And there is a tension between having enough CP violation to generate the right baryon asymmetry and having not too much CP violation so that we are killed by electrodipole moments. Okay, so this balance is all what it is for us model builders, so to say, to try to build a model that survives the situation. So this is a nice model, which I think is quite elegant, where, and I'm totally unbiased, as you can realize. So, so these actually, these are not my students. These are my collaborators. My students are coming later. So, so this is a model where we have the standard model sector where charge conjugation violation and baryon number violation occur through the sphalerons. And then there is a dark sector where CP violation is generated. And because CP violation is generated in the dark sector, it's much harder to communicate to our sector. It communicates at higher order loops, and it becomes, it can survive and have good connections with electric dipole moments. So this model has the minimal particle content is the standard model. It has a new U1 gauge lepton number, Z prime, and a new scalar. So the scalar here basically does the same job that I was telling you before, helps me to have a strong first order phase transition. At the same time, this scalar talks to the dark sector here and creates a CP asymmetry in the dark matter. And because this Z prime talks to the dark matter, which is a leptonic dark matter here, and talks to the standard model leptons, transmit this asymmetry to the lepton sector, and then the sphalerons transmit this lepton asymmetry into the baryon asymmetry. And of course, all the calculations are pretty involved, and I won't have the time to tell you. I could have, but I won't. But the important point to end is that you can look at dark matter, you can look at LHC, and you can look at gravitational wave signals. Okay, in this scenario, first of all, I was telling you we are computing here again the velocity, the bubble wall velocity as a function of the baryon asymmetry. There is, computing the fluid equations that describe the transport of these particle asymmetries near the bubble wall without making approximations that were made before in the literature for a small wall velocity, because velocities are not small. However, in this scenario, where I have my signals from this strong first order phase transition, there are different conditions. And unfortunately, the ones that are easier to detect are these orange ones that have to do with what we call detonation, where there is a runaway bubble. And so basically the plasma is not important, but the scalar dynamics is what is important. But this is when things happen too fast for baryogenesis to take place. Okay, so for those that are thinking about gravitational waves, you have to push lower, because all the models we get, we are in this area of blue for detecting first order phase transition gravitational waves that could work with electroweak baryogenesis, okay? So this is work to appear, and just to finish, I would say that there are two big things we are trying to work on. One is this work that we are really improving, as you realize, computing the effective potential for the scalar is what matters at higher orders. So we have done a higher order calculation because computing better the potential can change this and push it up, okay? So that's one thing. So we are doing that good job. The second job is, as I said, to compute for firm principle the bubble world parameters. This is going to appear with my former student and my current student. And then the other thing that is something I'm putting my toes into the cold water is to think about chiral asymmetries from the fermion bubble collision with quantum simulations. We are doing baby steps with 1+1 dimensions, but we are getting very interesting results. And there is a work to appear here. So concluding, baryogenesis is I think, one of the most compelling open problems or big questions in particle physics and cosmology. Baryogenesis electroweak baryogenesis is not the only solution, but it's particularly appealing because it has plenty of possibilities to falsify your models, or to get signals of your models. So I think that's really pretty interesting. So the electroweak baryogenesis, as I told you, requires new phenomena beyond the standard model that are at the electroweak scale. And mostly what it requires is new CP violating sources, and in most cases, new Higgs bosons, okay? And this provides targets for LHC and for electric dipole moment experiments. And in the model that I flashed to you in dark CP violation, there is also the possibility to connect electroweak baryogenesis to the dark sector. And I didn't have the time to go through, but this model has a very nice dark matter particle that is being searched for xenon NT and LC. Okay, so all for one, and thank you.
Okay, since we're short on time, I think we'll have to do with just one or two questions.
John.
You were planning to say something about supersymmetry, but you didn't have time. Could you say a little bit?
Yes, I can say that. So I don't need that. So I can say that actually supersymmetry, if you think about the minimal supersymmetric standard model, that the minimal case doesn't work either, because and it doesn't work not because it doesn't work because of the measurements we have done of the Higgs. So that's, I mean, the building that you have, you need the stops. The stops can have to be there, and it doesn't work. However, it's very easy to think about new CP violating phases in supersymmetry. And if you think about just the minimal SUSY extension plus one extra singlet, when you have phases, you can generate beautiful models of electroweak baryogenesis and dark matter, which are not at all contrived, okay? And supersymmetry, because of the way it comes, is a case where computing this nucleation temperature, rather than computing the structure of the potential, this critical temperature. So the issue of supersymmetry, the paper that I wanted to show, that I probably don't have the time, but let me just show it anyways. So what I want to say is that you can look at the vacuum structure. Doesn't matter, this is some parameter space, the Higgs mass and the other Higgs mass. So the things change drastically, because in reality, in supersymmetry, in these models, usually you have a high barrier and more distance between the vacuum, and for reasons I can explain offline. And so it is essential, it's a good message in this model, in this beautiful model of supersymmetry, that computing the nucleation temperature is crucial to see if you really can make the model work. So that's for supersymmetry. Alexei.
So I'm curious. You talked about phase transition being the, trying to make it be of the first order as required. What about in the same model, what about CP violation? I mean, have you thought about the possibility of making the theta, electroweak theta vacuum non-trivial? I mean, normally in a standard model, you can rotate it away with the chiral rotation. But if you mess up with the model a little bit, you can actually still have that as a viable source of CP violation.
You can mess up with the model in what is called, this would be like what I would describe, well, it depends on the language, but it's something that is called local electroweak baryogenesis, that it happens exactly at the bubble wall. And then you can have a theta, the equivalent of a theta vacuum. And there are people who have been working on that, not me, but of course would be other ways of thinking of using CP violation in models that are a bit different from this basic electroweak baryogenesis, because you have, I'm not an expert on looking at that, but I know that I have people that have been looking at that, and it's an interesting area of possible research where you just are thinking about the equivalent of a theta vacuum and trying to get the CP violation there. But that's all what I can say, because I have not looked at that in gory detail, but I know people have been looking at that.
Okay, at the risk of losing my welcome at Perimeter, I think we're going to have to move on to the next talk.
Yeah,
but I hope
you will be
take-
you will be welcome. You will be.
I hope you will continue the discussion with Marcela after the